The t-shirt that you've been wearing during the episode, which has this rather lovely Gibson guitar on it, is quite appropriate. And it is just a fluke that you've chosen that one, isn't it?
Yeah.
But we're actually going to look at sound on microcomputers.
Okay.
And we're going to use the Commodore 64 because that has the SID chip in it, which is quite interesting to look at.
Yeah, I think you've told me about it. Isn't it the best sound for any 8-bit?
I think so. We might get corrected in the comments, but I think it's one of the best sounds. Now, I know with this channel, the main thing I want to get out of it is I want you to have fun and maybe learn a bit at the same time. I know that what you want to get out of it is 1 billion subscribers. Yeah. But one of the little challenges, a side challenge if you like, that I've set myself is as I learn more about the programming, I'm starting to get it into my head that I think I could probably design a simple game. And probably I'll do it on the Commodore 64 just because of my fond childhood memories. And because I have a bit of a musical background, I think I could probably do some music as well. So I'm quite interested to learn how the sound works on a Commodore 64. It uses a SID chip, and if we go to the memory map up here, we can actually see that at location 54272 in our memory addresses, we get the beginning of the SID audio chip. And you can see that you have to control different bits of it a little bit like you would a synthesizer. Yeah. So for example, the waveform that's being produced, which is the type of sound as far as you're concerned, that's dealt with this particular byte at 54276. And you can, if you put in into bit 4 a value of 1, then you'll get a triangle waveform. Or if you want a saw waveform, then you put a 1 into bit 5 instead. So it's going back to that binary language thing. You can control the attack and decay of your notes, which is how quickly the note sounds and how quickly it fades away. And you can see that different binary values, so 0000, it will only last for 6 microseconds. And if you put in a value of 1, it will go for 24 microseconds. And so on, and you can actually use the bits and bytes to control how long the notes are lasting. So it's all super complicated but kind of super interesting at the same time. We're going to type in a little bit of code. I say a little bit, you'll probably think it's quite a lot, in order to make one note sound, and of course we will do this on fast forward for our friends.
Yeah.
Okay. So that's quite a lot, isn't it? If you compare it to your software, what do you use at school or on your phone to make that music that you make?
I use Maestro.
Maestro, okay. So on Maestro you can quite quickly build up a song, can't you? All different voices, different rhythms and so on. On the Commodore 64 we have to write all of this code in just to produce one note, and it sounds like this. Run. Try it again. And that's all the note that you get. Okay. Now, just to give you an idea of what's going on here, so at the top we're going into different bytes and we're poking values. So where you can see in line 10 that we've poked the value 15, that's actually volume. And in row 20 we've poked a value of 190, which sets the attack and decay for the note. And then we've got sustain and release, and we're choosing the pitch in row 40, so we're getting the right pitch that we want. There's also the waveform, which is value number 17 in line 50, and the duration is controlled with the 4t equals 1 to 250. The note was quite short, right? So if we wanted to make the note a little bit longer, then we can change the 250 maybe to, well, hang on, am I going to say something wrong here? Because if we put more than 255, perhaps it will be out of, they won't be able to hold the value. I don't know, this is where I have to learn about coding, because a byte can only hold up to 255, can't it?
Yeah.
Oh, but it does it. Okay, so maybe we can make that even longer. So Let's just try if we can make it 1,000.
Oh, Link.
Ah, okay. So now we've got a long note. Would you like it to be a little bit higher in pitch?
Yeah.
Okay. So let's make it, I think it goes up in semitones. What am I doing here? Let's try that up to 24. Now we've got 2 pitches because there's 2 pokes there, so this might clash. Okay, that sounds alright. Yeah? Should we change the waveform as well?
Yeah.
So maybe if we change the waveform to 33, we can get a different sound. Run. That almost sounds more like a violin, doesn't it?
Yeah.
Yeah? So that's... Okay, and then I've just got to try this as a last little test. I want to try making it, hang on, I want to try making it a lot higher in pitch. I'm going to make it 40, send it up like over an octave higher, and I want to make it really long. So I can make, maybe I can make this, let's make it 21,000 and see if it can run a long note like that. Okay. Well, that was quite long.
Yeah.
It kind of interrupts it, doesn't it? It's not a constant note. Every now and then it gives a little blip.
Yeah, good.
There. I don't know why that is. Maybe somebody can tell us. Oh, I'm bored. There we go. Right. Oh, I'm really happy with that. Now here's the thing that I don't know and that I want to learn personally. Like, that's one note, but you can make really nice polytonal music on the Commodore 64, and there's some really amazing examples in some of the games that you can get on the Commodore 64. I want to know how it's done, because I don't believe for a minute that people were sat there coding it all out like this. I just don't think that's what they were doing. They probably had a way of linking up a MIDI keyboard or something and creating music on a keyboard and then getting it into the computer. And I don't know how that's done, but I'd really like to find out. Do you want to join me on that journey sometime? Yeah? Okay, good. Right, there we go. Sound on the Commodore 64.